0.7 megapascal. The other one is 0.4 megapascal. Alright, so obviously to solve all this question, the main thing that you need to know is you have to find out whether the properties that you have is the stagnation property. So, or whether there are the stagnation properties. So, in this case, velocity is 150 meter per second. So these are not the stagnation properties. So stagnation properties will be the first thing that you need to find out. Alright, so of course you start with assumptions, and then so you use the previously established equation, the T naught equals to T plus B squared over 2Cp, to find the stagnation temperature first. Then based on the stagnation temperature, you use the isentropic equation to find the stagnation pressure. So this is a pretty standard steps here. Okay, so you found the stagnation temperature and pressure. So once you have found this, now what is the next thing that you should do? Whenever you have this kind of question, the very first thing that you need to determine is whether the back pressure is low, enough for the flow to be choked. Basically that. Because both methods, because both cases will give you different solution. So how do we determine whether you are getting a choke flow? You make use of the critical ratio. So you either find the pressure ratio compared to the critical ratio, or you sub the stagnation pressure in to see what is the critical pressure, and to see whether this pressure is lower than the back pressure or higher than the back pressure. Okay, so I go to the next page. Right, so usually my method I show what is the back pressure, so again you can just calculate the critical pressure, it doesn't matter. So in this case, if you calculate the back pressure ratio, you will see that this ratio is higher than the critical ratio. If you calculate the critical pressure, then you realize back pressure is higher than the critical pressure. So same thing. Alright. So if you calculate this, you will see this is 0.67. So 0.67 is larger than the critical ratio. So the flow is not choked. So if the flow is not choked, it means that at the exit, the Mach number is not 1. You are not getting pure sound. Right? So then what you can do now is just go to the table, check P over P naught. So now this P over here is 0.67. I don't know why I write 1 here, but yeah, it should be this value, right? 67. So to check the table, you will be able to get what is the Mach number at the exit. So the Mach number at the exit is 0.778, and the temperature ratio will be 0.892. So this temperature ratio, that T, is also the exit temperature, or rather the throat, the temperature at the throat. So then, based on this ratio, you can find the temperature at the, basically here, the exit temperature. So you can find the temperature, you can find the density. And then you can also get the velocity from the Mach number, because we know that Mach number is just velocity over c. So that Mach number over there, that you get square root kRt. So again, submit the equation, be careful of the 1000 of the r here. Then you can get the velocity, and then finally the mass flow rate. So this one I meant you don't really need to find so you don't really need to use the full mass flow rate equation, because that equation is very complicated. So you find one by one, even though question didn't ask for all this, but you use the temperature density, then find the velocity, then you use the mass flow equation, so you can get the mass flow rate. right? Okay, so if this case is this way, obviously the next case you are getting choke flow because this value is less than the critical ratio. So if you get choke flow, it means that your mass flow rate is maximum. Okay, you will get a maximum mass flow rate. So for this example here, I use the maximum mass flow rate equation. Then that is the mass flow rate that you can find. So similarly, let's say if you want, you can still use back this method, but in that case, your T will be T critical. So you can still do the same thing. You can still find T critical, find density critical, and then velocity is based on Mach number C, where your Mach number is 1. That is, so your Mach number is 1. They are the same equation. So you use mass flow equals to rho AV to find the mass flow rate. You will get the same answer. They are the same equation. Just that takes more steps, but for me it is less likely for you to make mistake because this equation is very long. But they are the same equation. Everyone can you understand? We will approach more similar type of question in the tutorial, but tutorial one will be converging diverging also, like we include the diverging type approach together. But method wise is all the same. Okay, so we look at one more example before we finish today's class. So air loss from a flat tire. So you might be thinking, what does this have to do with a nozzle? But technically, this is a nozzle. Okay, so air in an automobile tire is maintained at a pressure of 220 kPa gauge pressure in an environment where the atmospheric pressure is 94 kPa. The air in the tire is at an ambient temperature of 25 degrees Celsius. So there is a 4 mm diameter leak in the tire as a result of an accident. So you need to determine the initial mass flow rate of the air through the leak. So obviously we also know that this mass flow rate will change with time because the amount of air in the tire will change, will reduce with time, pressure will also change. But initially, what you have will be this pressure and this temperature. So this is an approximate nozzle as well because inside the tire looks something like this in this case. So this is the inside. And this is the and then with the hole, this is where it comes out. So this is in a way a nozzle because that hole is the change in that hole itself is the change in the area. So whatever, but obviously we know that inside here there is no actual flow. So this pressure and temperature you can treat them as the stagnation properties because velocity is 0 inside the tire. And your back pressure will be the atmospheric pressure, 94 kPa. So here, don't forget to convert. So always remember all your calculation is based on absolute pressure. So don't forget to convert the pressure to absolute pressure first. So you can see gauge pressure plus atmospheric pressure first. And then in this case, again, same steps. So we use the critical ratio, which is 0.5283, to see what is the critical pressure. So critical pressure is 166. Your back pressure is the atmospheric pressure, which is 94. So obviously, once again, you get choke flow. So then since you get choke flow, then you are using maximum mass flow rate. So for this question, we use like the long method to show you the calculation. So therefore the flow is choked. We know that velocity at the exit of the hole is the sonic speed. So then the flow properties at the exit count. Actually this is not property at the exit, but we need the density first. So this is the density at the inside. So this is the stagnation density first. So this is just alternate way. So the previous method that you saw just now is also applicable, but in this method, we first find the stagnation density. So why do we find the stagnation density first? Because then we can use the. Actually, I don't know why we find the stagnation density. Wait, let me see. Yeah. Oh, okay. Just that I didn't use the term here. So you use the density ratio equation. You submit the stagnation density. You can get the critical density. But similarly, you can also, just like the previous question, you don't actually have to find the stagnation density. Why? Because you can find the critical temperature. Then once again, you use ideal gas equation, PV equals to RT. You can find the density as well, critical density. So technically, you don't need. So this is just another way. Right? So again, you can use the critical temperature, just like the previous question. This question. You can actually find the critical temperature, then you use that temperature here to find the density. So both are applicable. Alright, then ultimately you can see exactly same steps. You have the density, you have the temperature, you find the velocity. Velocity will be speed of sound. Then you get the velocity, then you can get mass flow rate. Understand? Any question?